Hello, everyone, and thank you for joining us today. My name is Amy Hiltbeitel, and I will be your host for this NASA Technology Transfer Program webinar on additive manufactured alloys for high temperature applications. Our presenter today is Dr. Tim Smith. Dr. Smith graduated from Wright State University with a bachelor's degree in mechanical engineering in 2011. In 2016, he graduated from The Ohio State University with a PhD in materials science. He began his career at the NASA Glenn Research Center through the Pathways Internship Program in 2015, and currently his research focuses on the production, microstructural characterization, and deformation analysis of high-temperature alloys. He has contributed to 29 peer-reviewed journal articles, including publications in Nature Communications. Following Dr. Smith's presentation, I will be giving a short presentation on how NASA licenses technology to outside organizations. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box in the lower right corner of your screen, and we will answer them during the Q&A session at the end. At this point, I'm going to turn it over to you, Tim.
All right. As you heard, my name is Tim Smith, and I'm excited today to present two different technologies that we've been working on and we've developed here at the NASA Glenn Research Center. The first is titled the novel fabrication technique of oxide dispersion strengthened alloys, and the second is a specific chemistry that we've produced using that technique. So as you heard, a little bit, more background about myself. I graduated from Wright State University in 2011 with a bachelor's degree in mechanical engineering. In 2016, I graduated from Ohio State University with a PhD in materials science. Shortly before that, I started my career at NASA Glenn Research Center through the Pathways Internship Program. And since I've graduated from Ohio State, I've been working at Glenn, where my research is focused on the production, microstructural characterization, and deformation analysis for high temperature alloys. And I've helped contribute to 29 peer-reviewed journal articles, including some that have been published in Nature Communications and Nature Communications Materials. All right, so I think it helps to take a step back and present some of the background to why we ended up pursuing and developing the technologies that I'm going to show today. And it really came about through a collaboration with the combustion group here at NASA Glenn Research Center. Through discussions, they came to us and were, brought up the idea of being able to additively manufacture these new designs for combustor domes and nozzles. They thought that if they could, produce these new designs, it would lead to lowering NOx pollution, lowering the weight of the part, help improving the efficiency of jet engines. The issue they were having was that when they tried to 3D print these new designs with conventional materials that are commercially available, they couldn't sustain and operate the temperatures that this group wanted, which was temperatures above 2,000 degrees Fahrenheit or 1090 degrees Celsius. And so their main question to us was, is there a material that we can use to 3D print these combustor domes? And if not, can you help us try to produce the material? And of course, it sounded like a fun challenge. And so we said yes. A little bit of background about metallic additive manufacturing. There now is, multiple different processes and ways that you can 3D print metallic alloys. And each one has their pros and cons with it. Really, the method, AM method that we use for these technologies currently is laser powder bed fusion. And the reason we really concentrate on that was due to dimensional accuracy for the parts that we wanted to build. But like I said, there's a lot of other techniques, and the technologies we show here could possibly be used in those techniques as well. So when we started looking at the type of materials that we could use to produce this combustor dome, once you get above 2,000 degrees Fahrenheit, the list isn't very long. There's refractory metals, carbon-carbon composites, CMCs, your more conventional nickel-based superalloys that are gamma prime strengthened. And then another class called oxide dispersion strengthened alloys, which were researched, I think, heavily back in the 70s and 80s. The issue that we had with a lot of these material choices was, the application that we wanted to use the combustor dome in was in atmosphere, and so oxidation is a real concern at that high temperature. And so refractory metals, CMC composites, were an unlikely solution to that problem. Another issue with gamma prime strength and nickel-based superalloys is that they come with a lot of issues and problems when we try to 3D print them, especially the high gamma prime volume fraction nickel-based superalloys. And so that led us to kind of concentrate on, oxide dispersion strengthened alloys. Compared to, conventional nickel-based superalloys, they can operate at higher temperatures, which is, something that we wanted to concentrate on. But, as research kind of found in the 70s and 80s, the way we conventionally manufactured these was a process called mechanical alloying. And it was a very energy-intensive, time-intensive, and expensive process where you had to mechanically alloy metallic powder with your oxide, hope that you get a nice dispersion of it, hot compact it, heat treat it, machine it, and hope that your finished product has the properties and microstructure that you wanted. And many times it didn't, even after all that time and money. So we thought, hey, is there a way that we can maybe incorporate these oxides into our part during the additive manufacturing process and kind of skip all of those, expensive and time-intensive steps that we had to do, decades ago before AM, what was a process that we could employ. And so now we also needed to kind of pick a matrix metallic alloy to use for our 3D printing. And we, at least to start with, we kind of concentrated on these, a new class of alloys called multi-principal element alloys or high entropy alloys. And we were interested in them because there was a lot of reports coming out that they, overcame the strength and ductility trade-off, where you can have, great ductility and high strength, which is, something rare in metallic alloys. But in particular, we were interested in the nickel cobalt chrome medium entropy alloy due to what appeared to be a strong phase stability where it maintained a solid solution from melting to room temperature and was exhibiting, really nice mechanical properties. So these single phase solid solution MPEAs we believe we're going to be promising AM materials, also due to a minor difference between the liquidus and solidus temperature. And that narrow temperature range suggested that, we could limit dendritic segregation, solidification, cracking, residual stress in our AM parts. And so maybe this material could give us nice mechanical properties, but also some flexibility when we try to, 3D print it. And so now the question we need to solve was, how can we incorporate these oxides into the nickel cobalt chrome matrix without, pursuing mechanical alloying? As you can see on the image here in the lower right, after mechanical alloying, your spherical metal powder becomes very plate-like, it's deformed, and most likely your flowability of the powder is going to be hampered, and you're going to end up, finding a lot more defects in your build because of that. And so we wanted to really try to avoid using mechanical alloying for this step. And so for the study, we purchased micron scale nickel cobalt chrome powder that's really has the size cut for laser powder bed fusion. And we also got another powder batch that had small additions of rhenium boron, just to see if we can increase the high temperature properties of the metal a little bit with those additions. When we purchased nano-scale yttria powder with a size range between 100 and 200 nanometers, and our 3D printer that we use in-house is our EOS M100. So we can get some really nice small builds with that machine. And the whole aim for our initial study was, can we leverage laser powder bed fusion to produce ODS multi-principal element alloys for high temperature applications? And if so, let's try to, first figure out optimal laser parameters for both nickel cobalt chrome with and without oxide and the nickel cobalt chrome rhenium boron alloy with and without oxide. And if we could get 99%, 0.9% dense parts, explore the microstructural mechanical properties between the four different alloys. Further explore heat treatments and that effect on mechanical properties. And at the end, hopefully be able to produce a high temperature capable 3D printed combustor dome. And so this leads now to our first technology, and it's where we've incorporated this new high energy mixing technique that we're calling advanced dispersion coating, where we can successfully coat metallic powder with nanoscale ceramic powder. So basically what we do is we take nickel cobalt chrome powder that we purchased and put about 1% yttria into a container, and we mix it with this new acoustic mixing technique, that high energy mixing technique. And what happens is that nanoscale yttria coats the nickel cobalt chrome powder. You can kind of see here in a cross section cut of a coated powder, you get about a layer of 250 nanometers thick of yttria surrounding the nickel cobalt chrome. And the EDS kind of helps confirm that in the right there. Another way we can look at it is looking at nickel cobalt chrome powder before coating and after coating. And you can kind of see here, uncoated is on the left, the middle is coated. And really, we get this really nice dense coating on all our metallic powder after this coating step. And if you really zoom in, it kind of looks like we get some nice compaction of the yttria with also some loose particles on the surface of our metallic powder. And so what was really exciting was, one, it didn't deform the metallic powder. We still had very spherical powder after the coating step. And when we used Hall flow tests to explore the flowability of both pre and coated powders, what we found is that, at least qualitatively, it didn't appear to affect the flow of the powder at all after we coated it. And so we felt pretty confident that we were going to be able to put it in the 3D printer and actually work with the coated powder. Okay, and so through some trial and error and exploring laser parameters, we were able to successfully take that coated nickel cobalt chrome powder with yttria and produce dense builds with that, where the yttria gets finely dispersed throughout the build. And you can kind of see here on the SEM image, these really fine black dots. And through SEM-EDS, and we'll later show TEM analysis, those black dots are yttria oxide. And you can see they're finely dispersed through our build. They aren't agglomerated on grain boundaries. They stayed very fine, so we're at the nanoscale length scale in diameter. And so, initial microstructural calibration seems to suggest that we were able to produce these ODS parts. Here's just some more micrographs of the ODS material. Again, just a really nice fine dispersion of oxides, not agglomerating on the grain boundaries, and appears to be randomly dispersed. We imaged multiple areas, and we really don't see a variation in the density of these yttria oxides in our builds. It really does appear to be equal throughout our build parts, which was an exciting result. Okay, so for later in the study, we were able to successfully build 99.9% dense parts with AM nickel cobalt chrome without oxide, ODS nickel cobalt chrome with the yttria, and ODS with the nickel cobalt chrome with the small additions of rhenium and boron. What was interesting was when we tried to 3D print the nickel cobalt chrome with rhenium boron additions without the oxides, we actually ran into a lot of issues with microcracking. And if you remember, I suggested maintaining a narrow temperature range between the liquid and solidus temperature. What we didn't understand was when we added the addition of boron, we significantly expanded that temperature range and actually made a material that was much more difficult to 3D print. But what these results kind of appear to show, though, is that when we coated it with the yttria oxide, it appears to actually have made the material more printable, actually. And so when we look at mechanical properties moving forward here, you won't see any of the nickel cobalt chrome with just the rhenium boron without the oxide due to not being able to solve this microcracking issue. But we will see the ODS mechanical results. I'm looking at SEM-EDS, the nickel cobalt chrome ODS microstructure. This is after HIP. What you can see, nickel cobalt chrome maintains your random solid solution matrix, which is what we wanted to see and we're excited to see. And if we look at the yttrium and oxide oxygen maps, you don't see any large agglomerations of oxides or slag in our AM builds, which was an issue in some of our earlier processing parameter builds. So this is just kind of showing that we were able to solve that issue, and we just kind of kept yttria on that really nano length scale in these builds. If we look at the grain structures in these alloys, on the left here is nickel cobalt chrome as built, and you can easily make up, where those laser scans in that pattern was for our builds there. But after we did a HIP step, we were able to get a much more equiax grain structure through that post-processing step. What was interesting when we look at the nickel cobalt chrome ODS, after that HIP step, we don't see any type of recrystallization after that step, which actually surprised us initially, but suggests that we were successful in producing an ODS component through AM with this coating technique, because now we successfully pinned those grain boundaries, and even going up to high stress and high temperatures, we're not able to move those grain boundaries around. And so, but through XRD analysis, we were able to show that even though we couldn't recrystallize the microstructure, we are able to remove the residual stress in the component. And so it kind of gives us a good apples-to-apples comparison between the nickel cobalt chrome HIP. At least in those components, we don't have residual stress. And just a quick overview. This is just kind of showing an overview of the type of ultimate strengths we obtained with the nickel cobalt chrome with and without oxides here. And you do see a really nice increase in tensile strength at 1093 degrees C. And then the rhenium boron addition does appear to give us a small increase in strength as well. But you can see just by throwing in these oxides with this new manufacturing technique, we can obtain strengths that are above what you could get with your more conventional superalloys that you could either 3D print or would be used at these extreme temperatures. If we look at the creep rupture lives, you actually can see even more of an increase in improvement in our properties here. So just again, by incorporating that yttria in your build, you can see almost a 10-fold increase in our creep rupture lives in the nickel cobalt chrome with and without oxide here. And so, very, really encouraging mechanical results combined for microstructure. We felt pretty confident now that we have a process to efficiently produce, ODS alloys here using that coating technique. And I would like to show that we were able to, take the nickel cobalt chrome rhenium boron ODS powder and successfully 3D print a combustor dome with it. So just kind of shows that you can take, these coated powders and produce really complex parts and designs with it. All right, and so now this leads into our second technology, which, after we were able to convince ourselves that we can produce ODS alloys, we wanted to try to design a new MPEA alloy, built off the foundation of the nickel cobalt chrome work that we had done previously, and really, try to, accomplish a few goals. One, maximize our solid solution strengthening, while maintaining, a solid solution matrix after 3D printing and post-processing. We also wanted to try to add grain boundary carbides, specifically MC carbides, all while maintaining a narrow range of the liquidus and solidus temperatures for printability reasons. And again, we want to avoid TCP phase formation and intermetallic phases forming at grain boundaries as well. And we used a lot of thermodynamic models to come up with a new composition that we're calling NX-A10 right now, where we hoped we could achieve all of these goals. And so these are very boring optical images of NX-A10 after HIP, where we can basically just show, hey, it's almost virtually defect free. We can get really high densities, especially after HIP, and remove any type of defects from the AM build with this new composition. And when we started looking at SEM, after the HIP step. Again, you can see this very interesting AM grain structure in our new material, but we also start to see grain boundary phases starting to appear along grain boundaries. And if we kind of zoom in, you can see, you know, these dark phases along grain boundaries, and then you can also again pick up this really nice fine distribution of, you know, what we're hoping are those oxides in our build. When we go and did SEM-EDS, those grain boundary phases ended up being niobium and titanium-rich MC carbides. So, you know, exactly, you know, the type of phase that we were hoping to form along grain boundaries for improved high-temperature microstructural stability. And then when we look at the other elements in the EDS scan, what you see, you know, is, you know, no other phases really appearing, even after the HIP step. And so we've been able to maintain that solid solution with this new composition as well, which was exciting. And again, if you look at the yttria map, no large agglomerations of the yttria, and so we've maintained that fine dispersion of oxides. And so, at least from the SEM characterization, you know, it seems to confirm the predictability of these thermodynamic model predictions that we had done previously. You know, we were able to confirm the presence of niobium titanium-rich carbides along grain boundaries. The new composition maintained a solid solution matrix. There was no intermetallic or TCP phases that were observed. And again, we were able to avoid any type of bulk yttria or slag formation during our builds. So now we went ahead and did some TEM analysis of HIP NXA10, which interesting showed a, you know, even after HIP, a really high dense dislocation network, which we believe is due to the pinning of dislocations, you know, from the AM build with those oxides. And so even after the HIP step, we aren't able to get rid of those dislocations, at least at the temperatures and stresses that we are using at the moment. But again, you know, confirming that these oxides are finely dispersed and are doing a great job at pinning dislocations here, even at high temperature. If we do some EDS, STEM-EDS, you know, high resolution STEM-EDS, we can again confirm that these oxides are yttria and that they are, you know, very fine and uniformly dispersed throughout our microstructure. And interesting, you know, most of the other elements that in this new composition appear to not have reacted with the oxides, except for some instances where we see niobium or titanium coarsening of an oxide. But for the most part, the oxide is really just yttria in the matrix of this alloy. And so now we want to start exploring the mechanical properties, and I will show the mechanical properties of the nickel-cobalt-chrome builds and ODS and non-ODS from the earlier study as well here as comparison. At room temperature, NXA10 is the yellow curves here, and we're looking at as-built and HIPed. And, you know, at room temperature, the new composition, you know, does give us a nice bump up in ultimate tensile strength, you know, while maintaining, you know, the fundamental high ductility you achieve with these multi-principal element alloys. And so that was a really nice result. But really what we were interested in was the mechanical properties at 2000 degrees Fahrenheit, 1093 degrees Celsius. And you can see here now, you know, a significant, you know, improvement in properties at this temperature. The red here is nickel cobalt chrome without any type of oxide, and then green is just with the yttria addition. You can see, you know, a decent improvement in tensile strength and ductility just by incorporating those oxide particles at this high temperature. Blue is with the radium boron addition, and then yellow is NXA10, this new composition that we've developed. And you can see comparing nickel cobalt chrome AM where we started to NXA10, which is the composition we have now, you know, we've almost doubled the tensile strength with almost a 3x improvement in our ductility. And so we have a significantly tougher material now that we can 3D print and use at these, you know, high temperatures. And now we want to start looking at creep rupture, you know, which is usually, you know, a property that is, you know, dominates your materials at this high temperature. And we start at 20 megapascals. This is kind of just showing our previous creep test that we got. This small red curve here is nickel, cobalt, chrome. And we've also added a test of AM718 that was hipped and heat treated, just to kind of show what, conventional superalloys that are 3D printed a lot would do at these temperatures and stresses. And you can see nickel, cobalt, chrome, and 17 are pretty comparable in terms of, the length they survive at this high temperature. And then the blue curve here is, the ODS of radium boron. And you can see, a huge improvement in your creep rupture lives just by, small additions of radium and the oxides here. But when we compare those results to this new alloy, what you can see is that our NXA10 is performing far better than what these conventional superalloys or even our older versions of ODS alloys are performing. And it might even be hard to see, but these flat yellow curves here are the creep curves for NXA10. And in fact, these tests are actually still running as we speak. And so already, we're showing a 300x improvement over our AM nickel cobalt chrome, and over an 80x improvement over superalloy 17 in creep rupture life so far at the stress and temperature level. If we bump up the stress to 31 megapascals, again, these are our old creep rupture tests. Here, the red curves are nickel cobalt chrome, and you can see by just throwing in the oxides, you almost see like a 10x improvement in your creep rupture life, and you get an improved ductility as well. And then the blue curves here, radium boron additions, not much better creep rupture life, but some slower creep strain rates at least were achieved. But now, if we look at what NXA10 is able to do at this temperature and stress, you can see that, again, we've produced an alloy now that it is kind of in a class of its own compared to at least the materials that we were testing previously. And it's already, survived 1,000 times longer than the as-built AM nickel cobalt chrome at the stress and temperature level. And again, the test is still running as we speak. So now we move up to even higher stress, to 41 megapascals. At this temperature and stress, it really doesn't make sense to creep test 718 or your non-ODS materials. It's almost a tensile test, so it'll fail almost immediately. And so we're just comparing, our hipped NXA10 here to the hipped radium boron ODS. And you can see at this temperature and stress here, a 50x improvement in our creep rupture life. So a material that can, that can survive significantly longer, even at these higher stresses. And so again, to kind of go back to this, this overview graph, you can see, again, another nice bump up in tensile strength with NXA10 without really, changing the density of the material, which was, I think pretty remarkable. And if we look at the creep rupture lives, it really kind of shows how NXA10 is in a class of its own compared to, AM nickel cobalt chrome or even our older ODS versions. And so, we really feel that this material, might open some doors to AM components for high temperature applications that maybe weren't there previously. So to conclude, the first technology that I discussed was this novel fabrication technique for oxide dispersion strengthened alloys. I believe, we showed that AM can be leveraged to economically produce ODS alloys that until now had really been cost prohibitive. This advanced dispersion coating technique can successfully coat metallic powders with nano-scale ceramics. And a point that I didn't really make earlier in the slides was we strongly believe, and we have early results showing that we really can take almost any metallic powder and coat it with almost any type of ceramic. And so really, the design space of new materials is huge using this new coating technique. And we believe, and I think we showed in the second half that this new manufacturing technique combined with, multi-principal element alloys, I think creates a new design space for future high temperature alloys. The second technology that we showed was the development of NXA10 and how we use thermodynamic models to correctly, predict a stable solid solution matrix phase for the composition. SEM and TEM characterization both confirm this nice uniform dispersion of nanoscale oxides throughout the alloys build. And the high temperature mechanical testing of NXA10, reveals this surprising, superior results compared to our previous ODS alloys produced within this project, and compared to conventionally manufactured high temperature alloys. And so I'd like to acknowledge, there was a lot of work behind the scenes to help, get these studies up and running. And with that, I finished my presentation and be happy to answer any questions. And here's contact information if anyone's interested to speak further or have any questions they would want to send to me through email.